Bjørn Ekeberg, welcome to How the Light Gets In.
Thank you. Pleasure to be here.
So you're a philosopher of science with a strong interest in cosmology. What first sparked your interest in cosmology? And was it cosmology that motivated an interest in philosophy of science, or was it the other way around?
It was actually the other way around. I studied the historical and logical foundations for metaphysics. I was always interested in this crossing over between, like, the limit space between what we can know and what we believe. So the crossover where science and religion meet. And so I was digging into, I had a chance to research from different theoretical perspectives and overlap sort of history of how we came to construct our theories of the world and how we came to understand things in a modern scientific sense. And then increasingly I became focused on cosmology. It started with physics. I had my first research question was about the Large Hadron Collider and how we could possibly know or claim that an experiment underground in a tunnel outside of Geneva could somehow explain things at a universal level. And I just asked it very naively as an outsider, as a kind of question like, okay, what accounts for that? How do we know this? And so on. But gradually, as I did more studies of theoretical physics and those foundations, and then I became increasingly concerned with cosmology being, the most severely limited science from a scientific point of view, where it's most obvious that you have to make inferences and assumptions. And so I became very interested in how the science operates as a science and pretends not to do metaphysics. And so from that perspective, I was able to raise some critical or skeptical objections to the foundation of that as a science as well.
And how do you understand this kind of relationship between philosophy and science? Is philosophy there to kind of reflect on what this thing that we call science is and kind of dispel some false beliefs that people have about how certain science is, for example, or is there space for philosophy influencing, for example, how science is done?
Well, I mean, it's a product of a certain history, and this is what actually interested me in the first place: is how did we get into the situation where philosophy and science are almost like two solitudes? Because the actual foundation of modern science, before we called it modern science, in the 1700s and 1800s, it was called natural philosophy. Philosophy and science were very much aligned from the beginning, and all the classical scientists through James Clerk Maxwell up through Einstein would have some degree of philosophy background or something, and not just purely focused on physics. But something happened on both fronts in the 20th century, and you can start marking it back to around 1920s, 1930s. And on the physics side, there was a professionalization of physics, became a professional discipline where you would basically only learn physics and not so much philosophy. So physics set itself loose from philosophy. And at the same time, philosophy went through its own break. In a sense, it got kind of lost in the woods. And the tricky question for philosophy was what role it should serve or had to have relative to science. Because science was emerging as a new dominant way of knowing, increasingly had less use for philosophy. There was a famous or infamous debate between Einstein and Henri Bergson in the 1920s, which I take to be sort of the marker of where the shift happened between science and philosophy. Because Einstein and Bergson were basically debating the nature of time, and Bergson had a sort of a complementary view of time to physical time as Einstein described it, and was trying to advocate that there is a different model of time that is also useful. And Einstein, to put it crudely, had no interest in this whatsoever, and he says physics has no use for the time of philosophers. We have our own conception. So you could mark this as a time when physics kind of broke free of philosophy and broke free of metaphysics and took on the assumption that it's possible to do science without metaphysics. And then meanwhile, in philosophy, you had increasingly either an analytic school that were trying to be useful to science, and then the work of that kind of philosophy became focused on trying to clarify concepts and make scientific work better. And another camp that's sometimes called the continental school, which went wading into existential questions and things that had no direct correlate to science. So in my view, something was lost and broken in this, and that has persisted through almost a century of the lacking discourse between science and philosophy. A lot of the philosophy of the last 50 years has been either of these two. Either it's exists in a space that has nothing useful to say to scientists, or it's completely subservient to it and doesn't actually ask critical questions.
So a lot of your work when it comes to scrutinizing science, as you mentioned, comes in the area of cosmology, and in particular you talk about the standard model of cosmology. Mm-hmm. Can you tell us very briefly what that model is?
Yeah, the standard model of cosmology, it's sometimes called the lambda CDM model for the scientists who are deeply inside of it, sometimes the concordance model. This is a complicated beast, like I describe it as like multiple building blocks on top of each other. It's a multifaceted theory, but the core of it is a general relativity model that is evolutionary in scope, in time. There's a linear evolutionary model, coupled with this idea of a finite origin in time, with the Big Bang cosmology. And this came about in the 1920s and 1930s, and it was coupled with an insight or a discovery by Hubble that space appeared to be expanding. Now, this was an interpretation at the time of the phenomena that they were seeing, but it became a consensus interpretation that space is expanding, and here was a model that allowed for spatial expansion. So this model was very quickly, within a decade or so, was able to take over the entire sort of cosmological scene. Prior to this, we had a completely different view of what the universe would be like. But this mathematical model, coupled with this idea of a finite origin in time, or a cosmic explosion, which ran in parallel to nuclear physics, which was rising at the time, it captured the imagination of a lot of people, and it seemed to have a solid theoretical framework in that we have general relativity is able to predict extremely precisely within our own galaxy, or within our own solar system. And so what they did with this cosmology was to say, this is now valid for the entire universe, not just our own galaxy. And then as you started developing this further on this assumption, and we were able to make observations further and further out and discovering more and more and more galaxies, then more and more discrepancies started coming in. The observations that didn't fit with what the theoretical model said. So one of the most famous examples of this is dark matter, which emerged as an invention in the 1960s, 1970s to this problematic discrepancy that was showing up everywhere. And it was not just a small deviation, it was like a massive gap between what the galaxies appeared to be doing in the shape and the rotation curves and what the model would predict. And so the standard model of cosmology has, from this core, adding on a layer of dark matter, and then adding on another block called inflation to explain the beginning of time, how that's possible. And then further on, tacking on another block called dark energy to explain how possibly space is accelerating and not just expanding. Becomes kind of like a Jenga tower. It is built on a set of assumptions. Each of those blocks is built on a set of inferences that are very difficult to test. And so I think cosmology has ended up in a situation in the last century where it's become kind of stuck with a model that is failing to convince people that it could be the right one. And stuck in a pattern where it has to patch on every time it discovers a deviation. It seems to have to invent something new in order to account for it.
You've mentioned already, you've hinted at a couple of kind of critiques. How do you think of those? Do you think of them as scientific critiques, or do you think of them as kind of philosophical observations and philosophical critiques of the standard model?
I think the observations and the critique that I can come forth with is historically based, it's philosophically based, and it's trying to take an outside observer look in terms of plausibility of how well do we actually know how all these things stack together. But it's not my role to judge the merit of a scientific theory. That is for the scientific community. That is one consequence of physics and philosophy sort of breaking apart. So right now we have cosmologists, or scientists more generally speaking, are setting all the terms for how to approach and understand the universe. And they're also the ones who judge whether they think a theory has more merit or not. To some degree, the core of the model is taken as a matter of faith. And that if you are to question it then you risk running afoul of a lot of things regarding, funding and career and so on. On the one hand, especially if you are a scientist, you can build a career now on challenging some of the upper blocks, so to speak. For example, dark matter. There is a real challenger to this particular part. But I find very few scientists are willing to look at the more questionable assumptions underneath the core building blocks of how we got here in the first place. And the reason why it strikes me is not because those blocks are so solid and proven beyond doubt when you look at them closely. It's more that if you are to put them into doubt, or if they are slightly wrong, or if you are to remove them, then you lose the guiding structure you have to make sense of the universe. It's like taking a framework away from a scientist is the same as making them blind. Like, then we have nothing to guide us by. So I think that there's a tendency to want to cling on to the basics because it becomes very difficult to do scientific research. It is much more convenient to add things to the model and preserve the existing structure than it is to radically rethink it.
So in connection to this, in a recent interview, you argued that the standard cosmological model relies on metaphysical assumptions. But it didn't sound like you meant that necessarily as a critique.
I think it's impossible to create a cosmology or to have a cosmological understanding without having made some metaphysical assumptions to begin with. So even competing models before the Big Bang Theory, there was something called the steady state theory that was competing for a little while with the Big Bang Theory, had its own metaphysical assumptions. This whole, which was in that case an unchanging universe, so whatever we observe as changing is actually being recreated elsewhere. But it's one of the legacies of the split between philosophy and science in the 20th century is a strand of thought sometimes called logical empiricism or positivism, which really greatly influenced science into this rise of the professional school of science, is to believe that science has to be free of metaphysics, and that it's the ideal is to have a science that's pure without having to make any such grounding claims or any such framing devices. So in my view, this is a delusion, and it would be much better if we could speak openly about what the guiding assumptions or the premises for a theory are, and speak about them openly instead of trying to hide them away. If you look at scientific texts or any scientific calculation, if you look at Einstein's own work on general relativity, he has a couple of pages describing the assumptions or the principles that he uses, and then there's pages of mathematical equations. Now, most physicists would be trained to look at his math and then to train to look at the field equations and to kind of gloss over the assumptions part. But all of those assumptions are themselves up for debate or questionable. They're ways of framing the problem, and I don't think you can ever get around that. One very important principle that connects general relativity to, like, creates a cosmological model for it, is known as the cosmological principle. And that sounds very elevated and fanciful, but it's really just to say that the universe is the same in all directions. And its main function is to be useful as a simplifying assumption.
Is this cosmological principle the same as saying there are laws of nature that apply everywhere, or is it a slightly different assumption?
That's an even more fundamental claim, and in a way that is one of the key tenets of standard cosmology, is to say that what we know with high confidence within our own solar system, the laws that we have been able to deduce from our little tiny corner of the universe, they apply across the universe. And this may have made a lot of sense in the 1920s, 1930s, and so on, when this theory was under formation. But as we have learned more about the size and the scope and the vastness of the cosmos, it becomes more and more untenable, and the number of contradictions start piling up as well. There is something about this. There's something about this core assumption that the laws we have here apply all across the universe, which ultimately rests on a kind of faith in that mathematical laws are the same everywhere. They increasingly come under scrutiny from empirical data and observations.
Would it be possible to tell the difference, though, when we have observations that seem to contradict what we think are laws of nature, would we be able to tell the difference between whether that means our laws of nature are just wrong, or that just that bit of the universe that we're observing has different laws of nature? Could we tell? Could the data alone tell us whether one or the other was the case?
That's an interesting question. I think that's where it becomes difficult with cosmology, because we lack clear guideposts for how large of the scale is the scale. Part of the way that we understand just the sheer space alone and how we measure it is we use light phenomena in the sky, certain stars or standard candles, to use them as guides for understanding how far they are away. That in itself is theory dependent. And especially if you look at something like supernova explosions are now used as part of a guidepost to indicate how far is it to galaxies that are out in space that far. The further out you go, the more model dependent you become. Like you could have huge variations of just the scale itself, depending on which model you choose to calculate by. To put it this way, we are a little bit lost in the dark without anything other than a map to guide us. And even if we know the map is incorrect, throwing the map out is also something that most scientists would be reluctant to do, because we don't know quite what to put in its place. So fumbling in the dark like this, it gets fuzzy the further out you go.
What will the shift that you're envisaging mean for how we understand our place in the universe and what the universe is like? Is it going to turn out to be an even stranger place than we think it is now?
I mean, this is the interesting thing. The shift that I was trying to describe, I think, could be phrased as we become better at mathematical descriptions. So we can create models that better fit with observations, that can add in variability for certain factors we thought were universal before. But what we will end up with in this vision is better and better approximation between, like, we have a complex theoretical model that aligns better and better with observations. But what we're lacking is explanation. So if you take away dark matter, for example, and you insert this Challenger modified Newtonian dynamics, you change the laws of gravitation instead, and you say dark matter doesn't exist, but here we tweaked the laws of gravity to make the observations fit. One of the risks surrounding the science and the development of the science, and I think the public is very interested in cosmology, generally, it seems to me. But it's very hard to access the theory on a level that is understandable, and it's almost not understandable to astrophysicists or cosmologists themselves. There's a lot of questions at stake that I think also need to be addressed, and maybe that's a space for philosophy to enter as well. But I don't think scientists can explain.
So thinking about philosophy of science and cosmology is one aspect of what you do. Another aspect is you write dramas and thrillers for film and TV. Mm-hmm. Have you ever thought about merging your creative writing interest with your interest in cosmology?
I never liked science fiction growing up as a category. I found it is why it was curious to me. I started becoming interested in physics and metaphysics and astronomy and cosmology. It was not from, I grew up with the remnants of the space age kind of filmatic universe, and it never spoke to me. It always struck me as being false somehow. I should say that the work I do on the side of being a philosopher of science is really because there is no career path. I found out at some point that doing all this research, it would lead me to unemployment or frustration or just a very marginalized existence. I didn't think that was the right outlet for this kind of research.
Does philosophical thinking inform your creative writing in any way?
They are in practice very separated, but I do believe that they integrate on some level that I have yet to quite see. I was told before going into philosophy and warned about ever spending time doing philosophy is that it's very intangible knowledge. It's not obvious how it can be put into economic use, for example. And I used to think that a lot of my studies on, logical and historical foundations of how this came to be is something that is of no particular value to anyone. And then I realized as I engage more with physicists community that they're not trained in this kind of thinking at all. And that there might be, if there is dialogue here, there might be something to contribute.
Bjørn Ekeberg, thank you very much.
Thank you.